Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of this topical MCQ on what I classify as topic 4 that's under states of matter and all those gas laws as well as ideal gas equation. So in the previous part of the series, it's supposed to be a 5-question series, but I think I accidentally omitted the question 9 and 10, so I'm going to include this as a 7-question series. That's including question 9, 10, and then from 11 to 15 as usual in this kind of 5-question series, right? So without further ado, let's get started on this. So this is an ideal gas equation. So we need the PV equal to well, it's probably best if I write down PV equal to nRT. So you know PV equal to M over mRT. From there, you can rearrange. So do not try and put in value before you rearrange your equation first, right? So from those equations, you gotta think about the unit very carefully. So the mass over mR, the mass is in gram. So that's the mass of the gas. It's already in gram. And the R is just 8.31 joule per Kelvin per joule per Kelvin per mole. Okay, from your data booklet. And then P is already given in Pascal. So 1 Pascal equal to 1 Newton per meter square. And that is the standard unit, Newton per meter square in this equation. So there's no need to convert it or anything. So that is the same as 1.0 times 10 to the 5 Newton per meter square. Your concern really is this thing, the volume is in cm cube. So when you have something in cm cube, you have to convert it into dm cube, meter cube. So 1 cm is 10 to the power minus 2 meter. If you cube both sides, so I use bracket because what I'm doing on the left, I'm doing on the right as well. That's the meaning of the term equal, which I'm sure you know from your primary school mathematics. All right, so 10 to the minus 2 cube meter cube. So 1 cube is 1. 10 to the minus 2 cube is 10 to the minus 6 meter cube. I can get my relationship without even remembering anything, starting from basic and doing the simple maths, yeah? So I never try to memorize this thing because, you know, I could get them from scratch and I know I could always get them from scratch easily, all right? So it's 10 to the minus 6 because we're going from a smaller unit to the bigger unit. As you see, if we do this correctly from the very first step, we can get them correct into the final step. So what we're doing is here 0.10 times 8.31. Oops, I forgot there's a temperature. It's given in degrees Celsius. So you need to convert that to Kelvin. So that will give you 300 Kelvin. So 27 Kelvin there is incorrect. So A is incorrect. They use 83.1 without converting it to meter cube. That's incorrect. There is 37 again. So they didn't convert that to Kelvin. That's incorrect. D has to be the only option there. It turns out that without even converting this to meter cube, you could have gotten it straight away by knowing that you cannot use 83.1 immediately as cm cube. You have to convert it. So yeah, without doing this conversion, you have gotten this straight away. But again, you need to know this how to do it in theory paper, yeah? Next bit is asking you which gas is likely to deviate most from ideal gas behavior. So this is the one where you have non-negligible intermolecular forces, because that's when you will break the assumption the most, right? When you think about van der Waals, all of them will have van der Waals, but this one has the least number of electrons, only 2 electrons. The rest have more electrons, so this is going to be the one which has weakest van der Waals. In fact, this is going to be the most ideal out of all 4 of them, alright? When you think about permanent dipole, HCl is a polar molecule because of this difference in electronegativity. CH4 is a non-polar molecule because, well, you got a tetrahedral geometry where you have the 4 bond pair repel equally, and you have the 4 atoms are exactly the same, so the dipoles get cancelled out. So there's no permanent dipole. There's no permanent dipole there because, well, it's single atom, so we call monoatomic. Okay, N2 again is non-polar because, well, well, it's just the same electronegativity, right? So this is going to be the one that has the strongest intermolecular force. In addition to van der Waals, you also have permanent dipole, which are stronger than just van der Waals for all of these, all right? So that is the least ideal. Okay, whereas this one is the most ideal because amongst all these three, this is the one with the weakest van der Waals, which depend on the total number of electrons in the atom or the molecule. All right, between this and this one has got 7 plus 7 is got 14 electrons. This one has got what is this? 18 electrons. No, sorry, 16 electrons. Oops, no, not 16 electrons. I beg your pardon. 6 electrons from carbon, 4 electrons from hydrogen, and you will get 10 electrons. But actually, this one has weaker van der Waals than this, and you can tell because this one is bigger size. Van der Waals depends on two factors: total number of electrons, which a lot of students remember, but they forgot about size, which is also equally important as well. This is a bigger molecule than just this, which consists of 2 atoms, all right? So it's not just one factor, but it's the other factor as well. You can check their difference in boiling point and you can tell, all right? So this next question is another ideal gas equation, but here you're given in dm cube. This is in degrees Celsius. This is already given in mole. So PV equal to nRT, so I don't need to do anything about the number of mole there. So pressure is nRT over V. Temperature first, that is in degrees Celsius. Convert that to Kelvin, then you will get, well, 273 plus 273. That's what you want. You do not want 273 there, okay? Because that's in degrees Celsius, all right? So I don't want to evaluate it because there's no point of evaluating it, okay? So A and C are out. Okay, very obvious choices there. Next up, you also have this volume. We talk about the volume has to be in meter cube. So how can I convert dm cube to meter cube? 1 decimeter is equal to 10 cm. So this is called decimeter. Okay, so 1 decimeter, if you convert cm to meter, you divide by 100. I'm going to get 10 to the power minus 1 meter. 10 over 100. 10 cm convert to meter, you divide by 100, you're going to get 1 over 10, which is 10 to the minus 1 meter. Cube both sides. This is another primary school mathematics, which I hope you know what I'm doing. I do whatever I do on the left to whatever on the right. Okay, I cube both sides. 1 cube is 1. 10 to the minus 1 cube is 10 to the minus 3 meter cube. So volume is 3.0 times 10 to the power minus 3 meter cube. There you go, 10 to the minus 3, all right? So people will get confused if they get the unit conversion wrong, yeah? Next question is about electrical conductivity property of solid and the liquid. So when we look at all of these are considered quite high melting and boiling point. They cannot be simple molecular, which, again, none of these are simple molecular, all right? What else can I say? These ones, they do not conduct when solid, but when they become liquid, they conduct very well. So judging from these, you can tell that there is no free ions. Okay, because looking at R and S, these are all ionic compounds. All are giant ionic. Because all of them are giant ionic compounds, so I talk about no free ions to conduct in the solid state. But then you can conduct when they are liquid, all right? And then the last one, it can conduct when it's solid already. It can conduct when it's solid. Well, copper can conduct when it's solid, all right? Because it's a metal. Metal can conduct when it's solid. SiO2 cannot conduct when it's solid because it's giant molecular. Well, not just because it's giant molecular, because, you know, it hasn't got any free electrons at all when you think about the structure. Okay, it looks like that. Each silicon is bonded to 4 oxygen, and each oxygen is bonded to two silicon, all right? So there are no free electrons at all on the silicon to conduct, unlike in graphite. Of course, graphite is the only one that can conduct when it's solid out of this option, well, including copper. So diamond is out, so meaning B and D are out. And then you have to decide. So I'm not worried about A and C now. For T, I'm worried about R and S, okay? Look at the melting point and boiling point. So S have much higher melting point and boiling point than R. Because this is an ionic compound, you need to think about the strength. The strength of ionic bond depends on the cations, depends on the anions. Okay, we talk about charge density of cation. So that is the charge, that is the size. Okay, we talk about charge density of anion. That is the charge, that is the size. All right, so obviously we want a stronger ionic bond for S because it's got a higher melting point and boiling point than that. When you look at NaF and KCl, so K plus is going to be bigger than Na plus, Cl minus is going to be bigger than F minus. So you can tell that KCl is going to have a weaker ionic bond than NaF. So KCl should have a lower melting point and boiling point than NaF, and that is not the case here. All right, S have higher melting point and boiling point than R, so I can cross out A, meaning to say C must be the only correct option, because as you could see here, Mg2 plus is more charged, higher charge than Na plus. Mg2 plus is smaller than Na plus, stronger ionic bond. O2 minus is higher charge than Cl minus, 2 minus versus minus 1. O2 minus is smaller than Cl minus. Okay, think about second period shell completely filled. Think about the third period completely filled. Well, second period versus third period, you can tell which one is bigger straight away. Yeah? These are the factors you learn in AS structure and bonding. What factors govern the strength of ionic bond? All right. Next bit is asking you which one do you break hydrogen bond. So you need to break hydrogen bond. All right. So there's going to be endothermic. When you go from what am I doing here? Here I can go straight to D first. You are breaking each and every one of the CH bond and you are forming atoms. This is atomization, as you will learn it in the next topic on enthalpy change. That is not breaking hydrogen bond, that is breaking covalent bond. So you break covalent bond here. Each of these covalent bonds are broken, and there is not hydrogen bond that is being broken. The same deal here, you are breaking, this is a group 17 chemistry. When you think about it, you have two of that molecule, and you break it, and you will form HH and II. Of course, you also reform the HH and the II in covalent bond, but you need to break that. Okay, and that is not hydrogen bond. Again, that is breaking covalent bond. Okay, between A and B, B is definitely the answer because, well, you know, H and H, only van der Waals. There's no permanent dipole, there's no hydrogen bond. So you're just breaking van der Waals to go from H2 liquid to H2 gas, whereas you have hydrogen bond between the NH3 molecules in, well, NH3, okay? This kind of question again, least resemble an ideal gas. So this is the one where the intermolecular force is the least negligible. Least negligible, meaning it's the strongest. Okay, we are looking for things that can form hydrogen bond or permanent dipole. Between all of these, I can tell you ammonia is the one, because if I'm running out of space at the top there, so I'll just think about van der Waals. All of them will have van der Waals, okay, because all of them have electrons in the molecules. Helium versus hydrogen. When you think about helium, it's just like that, and H and H is like that. There's 2 electrons and 2 electrons altogether. But as I mentioned earlier, van der Waals depend not just on total number of electrons, but depend on the size as well. There's a second factor, yeah. So this has smaller size because it's single atom. So this is the weakest van der Waals. This is the most ideal out of the 4. When you compare these two, this is the most ideal because it's got the weakest van der Waals due to the smaller size compared to this diatomic molecule. Yeah? In terms of permanent dipole, trichloromethane is polar, ammonia is polar, none of that is. But then there's a stronger form of permanent dipole, which only ammonia has, which is hydrogen bond, where you will be expected to show your hydrogen bond from the lone pair to the other neighboring delta plus hydrogen, like that. And that's how you show it. Okay. And of course, trichloromethane, you don't have a hydrogen bonded to oxygen, fluorine, and nitrogen, cannot form hydrogen bond. So, you know, it's stronger than van der Waals, but it's not as strong as hydrogen bond. All right. This is the last question of this. I was going to say 5-question series, but this is a weird one because of my mistake by omitting the question 8 and 9 from the previous question. So this is a 7-question series in this particular video. All right. So what are the lattice structures? So this is basically a stating question, and these are per your AS specification, your syllabus content, where you need to know the structure of diamond, iodine, and silicon 4 oxide. Diamond looks it's basically just carbon, right? So it's a carbon sp3 throughout. Iodine is just a simple molecule. Silicon 4 oxide, I think I showed you earlier, SiO2 is going to look like that. SiO2 is going to look like that. Each silicon is bonded to 4 oxygen, 109.5 degree. Each oxygen is bonded to 2 silicon throughout a giant molecular network. So each oxygen there has 2 lone pair and 2 bond pair. It's going to be 104 or 104.5 degree. Okay. So SiO2 is giant molecular. Okay, so there's giant molecular. This is a diamond. It's also giant molecular. Does not conduct electricity, unlike graphite, which is the other allotrope. Allotrope is just a different form of the same element. Yeah, this is simple molecular. So very straightforward there. It's just about knowledge and stating kind of question. This is what we call the chemistry vocabulary. The more you know, the better you will get at it. All right. So this is the end of this tutorial video on these multiple choice questions for topic 4. If you enjoyed this video, please subscribe to the channel and spread the words among your friends and colleagues and class chat and whatever. Okay, so I'll see you in the next video. Thank you for watching.